Santa Barbara, California, Los Cumbres Observatory, early 2025. Joseph Farah is a fifth-year graduate student in astrophysics at UC Santa Barbara. He has been given a dataset from a supernovae discovered in December 2024, catalogued as SN224F, located roughly 1 billion light-years from Earth, or more precisely, about 327 megaparsecs, which works out to approximately 1.07 billion light-years. It had been flagged by the LGO2 survey collaboration and classified by ePesto Plus as a Type I superluminous supernova in January 2025. One of the brightest classes of stellar explosions known, at least 10 times brighter than an ordinary supernova, bright enough to briefly outshine every single star in its host galaxy combined. Farah works with the Los Cumbres Observatory, which is not the kind of observatory most people picture when they think of cutting-edge astrophysics. There is no single enormous telescope atop a remote mountain. Instead, Los Cumbres operates a global network of modest-sized robotic telescopes, instruments in the 1-meter range, smaller than the giants of modern astronomy, coordinated across sites in the United States, Chile, Australia, Spain, South Africa, Israel, and other locations. The network is specifically designed for time-domain astronomy, the study of objects that change over time, for observing the same patch of sky repeatedly, from different longitudes as the Earth rotates, so that a target can be monitored around the clock without the gaps that daylight or bad weather would impose on any single site. This continuous coverage is not a luxury. For a class of objects where the timing of brightness variations can encode the physics of what is happening inside the explosion, the ability to measure THOS variations without gaps can be the difference between detecting a pattern and missing it entirely. Farah's job is to analyze the light curve, the plot of how the supernova's brightness changes over time. For most supernova, the light curve is a relatively smooth shape. It rises as the explosion expands, peaks, and then fades. For superluminous supernovae, the shape can be more complicated, sometimes with bumps or irregularities on the way down. These bumps have been noticed before. Nobody has had a fully satisfying explanation for them. Farah looks at the light curve of SN224F. The bumps are there, but there is something unusual about them. They are not random. They are not irregular. They are repeating over and over at intervals that are changing in a very specific way. Each bump arrives a little sooner than the last. The time between bumps is shrinking, not randomly, not approximately, but following a smooth mathematical curve, decelerating in a way that Farah has seen before, just not in a supernova. He has seen it in gravitational wave data. The signal produced by two black holes spiraling together just before they merge. That signal is called a chirp, named for the sound you would hear if you converted the pattern to audio. A tone that rises in frequency until the moment of merger. It is one of the most recognizable signal shapes in all of modern physics. The light curve of SN224F is chirping, a supernova, 1 billion light-years away, whose brightness is oscillating in a pattern that accelerates in frequency exactly the way a gravitational wave chirp does. Farah stares at the data. Then, he begins building a model. What he finds, after months of analysis and collaboration with theorists, including Logan Prust, then a postdoctoral scholar at UCI Kavli Institute for Theoretical Physics, is that only one explanation fits both the period of the signal and the rate at which that period is changing. Not simple Newtonian mechanics, not the magnetic fields of the neutron star, not any of the standard models previously proposed for supernova light curve bumps. The only model that fits is general relativity. Specifically, a spinning dead star, born in the explosion, twisting the fabric of spacetime itself, causing a disk of material to wobble in a way that no other force in the known universe can produce with precisely this mathematical signature. The paper was accepted by and published in Nature in March 2026. In it, Farah's team wrote that this is the first time general relativity has been invoked to describe the mechanics of a supernova. For decades, general relativity has been tested in extreme environments. The bending of light around the Sun, the orbit of Mercury, the merger of black holes detected as gravitational waves, the shadow of Sagittarius, a asterisk, imaged by the Event Horizon Telescope E. Each test confirmed that Einstein's equations work, even in conditions of extreme gravity. But every one of those tests was about the spacetime environment around a massive object, not the internal mechanics of a stellar explosion. The distinction matters. When LIGO detects a gravitational wave, what it detects is the ripple in the geometry of spacetime produced by two merging objects, a consequence of general relativity's description of how mass curves spacetime, propagating outward d from the source. The merging objects produced the ripple. The ripple is the signal. The theory describes the spacetime geometry of the source, not the internal mechanics of the merger itself in any way beyond the gravitational radiation it produces. When the Event Horizon Telescope images a black hole's shadow, what it images is the geometry of spacetime around the black hole, warping the path of photons in exactly the way Einstein's equations predict. The black hole creates the geometry, the photons carry the image. The theory describes the space around the object, not what is happening inside it. SN 224A FAV is the first time general relativity was used to explain not just the space around an object, but what the object is actually doing inside a supernova, how its spin is dragging spacetime, how that dragged spacetime is making a disk wobble, how that wobble is periodically blocking and reflecting light in a pattern whose mathematical fingerprint is unmistakably Einsteinian. The dead star was not just emitting signals. It was encoding general relativity into its own light curve. This video is about SN 224A FAV, a superluminous supernova discovered in December 2024, and the chirping signal inside its light curve that revealed, for the first time, a newly born magnetar using general relativity to power one of the brightest explosions in the universe. It is about what a magnetar actually is, how it forms, and why the standard model of superluminous supernova had been producing light curves that nobody could fully explain for years. It is about lens-Thirring precession, a prediction of general relativity that describes how a spinning mass drags the fabric of spacetime with it, and what that effect looks like when the spinning object is a neutron star with the mass of the Sun compressed into a sphere the size of a city. And it is about why this specific discovery, a chirp rather than a steady pulse, is the proof that had been missing for 16 years from a theory first proposed in 2010. By the end of this video, you will understand what a magnetar is and why it matters for the brightest explosions in the universe. You will understand what lens-Thirring precession is, in terms that do not require a physics degree to follow. You will understand why the chirp in SN 224A FAV is a different kind of signal from anything previously observed in a supernova. And you will understand why this particular piece of evidence, a signal whose mathematical pattern could only be produced by spacetime itself bending under the weight of a spinning dead star, represents something genuinely new in our understanding of how extreme physics actually works. What is a superluminous supernova, and why are they so much brighter than ordinary supernova? What is a magnetar, and what makes it fundamentally different from an ordinary neutron star? What is lens-Thirring precession, and why does it produce a chirping signal rather than a steady one? Why had the theory that Magnetar's power superluminous supernova been proposed 16 years before this discovery without being confirmed? And what does it actually mean to say that general relativity is describing the mechanics of a supernova from the inside, rather than just the spacetime around it? This is not a video about mysterious, unexplained phenomena. The signal in SN224A5 is not mysterious in the sense of being inexplicable. It is mysterious in the original sense of the word, something profound, something that required the deepest theory in physics to explain, something that was sitting in supernova data, waiting for someone to ask the right question. This is also not a video about a minor technical detail in an obscure field. Farah's team explicitly describes this as the first time general relativity has been invoked to describe the mechanics of a supernova. That is a statement about a genuinely new application of the best-tested theory in physics, not a refinement of an existing idea, but a first. The honest version of this story is exactly what makes it worth telling. A graduate student noticed something in a dataset that did not fit any existing model. He found the one thing that did fit, and the thing that fit was Einstein. Before we go further, if the idea of a dead star encoding general relativity into its own light curve is the kind of story that pulls you in, subscribe to Galaxy Pulse. We find the real science underneath the headline and explain it carefully. Now, back to SN224A5, and the signal that should not have been possible to explain without bending spacetime. To understand why the chirp in SN224A5 is significant, you need to understand three things in sequence. What a superluminous supernova is, why magnetars were proposed as the power source but never confirmed, and what lens-Thirring precession is, and why it produces a chirp rather than a steady signal. All three of these build on each other, and the payoff of understanding all three is the ability to see exactly why this specific observation is different from everything that came before. Supernova are the explosive deaths of massive stars. When a star, roughly 8 to 30 times the mass of the Sun, exhausts its nuclear fuel, its core collapses under gravity in less than a second, and the outer layers are blown away in an explosion that can briefly outshine an entire galaxy. These are core collapse supernova, the kind that have been observed, studied, and modeled extensively, whose physics is well understood in broad outline. To appreciate how extreme this process is, it helps to put numbers to it. The collapse of the core, from a sphere roughly the size of Earth to a neutron star roughly 20 kilometers across, happens in less than a second, generating a shockwave that propagates outward through the star's remaining layers at tens of thousands of kilometers per second. The total energy released is staggering. Roughly 10 to the power of 46 joules, or about as much energy as the Sun will radiate over its entire 10 billion year lifetime, released in a fraction of a second. Most of this energy is carried away by neutrinos, ghostly, nearly massless particles that barely interact with matter, and only a small fraction, around 1%, is deposited into the expanding material. It is that 1%, combined with the decay of radioactive nickel-56 synthesized during the explosion, that powers the visible light of a typical supernova. But in the early 2000s, astronomers began finding a class of supernova that did not fit this picture. They were at least 10 times brighter than any standard core collapse supernova. Some were 100 times brighter. Their light curves rose more slowly, peaked at extraordinary luminosities, and declined more gradually. They were found at a range of distances, but were especially common in small, metal-poor galaxies, galaxies that had formed stars rapidly and contained relatively few heavy elements, conditions that affect how massive stars evolve and die. They were rare enough, and observationally challenging enough, that assembling a statistical sample took years. These were named superluminous supernova, and they became one of the central unsolved problems in stellar astrophysics. Not because their existence was hard to accept, but because nobody could figure out what was powering them. An ordinary supernova is po-werde primarily by the radioactive decay of nickel-56, a nuclear product of the core collapse, and by the shock wave that propagates through the star's envelope. But the luminosity of superluminous supernova exceeded what these mechanisms could plausibly produce by factors of 10 to 100. Something else was providing energy. The puzzle was made more acute by the way this extra energy was delivered. It was not delivered all at once, like an additional burst. It was delivered gradually, over days to weeks, in a way that sustained the supernova's luminosity at an extraordinary level for far longer than the standard mechanisms could explain. Whatever the additional energy source was, it was not a single explosive event, but an engine, something that kept pouring energy into the system long after the initial explosion had faded. In 2010, two physicists, Daniel Kaysen at UC Berkeley and Lars Bildsen at UC Santa Barbara, proposed an answer. What if the collapsing core did not simply produce a neutron star, but a specific and extreme kind of neutron star? A magnetar. And what if TH at Magnetar was spinning extremely rapidly, hundreds of times per second, depositing its rotational energy into the surrounding supernova ejecta through its intense magnetic field, effectively acting as an engine, pouring energy into the explosion from TH inside over days and weeks, rather than milliseconds? In this model, the magnetar's spin energy is transferred to the ejecta through magnetic coupling, and this energy input is what powers the extraordinary luminosity of the superluminous supernova. The model was compelling. It matched the rough brightness and d-duration of many observed events, and it quickly became the leading hypothesis for what powers superluminous supernova. It is worth pausing to note why the Kaysen-Bildsen model was taken seriously so quickly. Despite being a relatively simple proposal for an extremely complex phenomenon, the appeal of the Magnetar model was not just that it could produce enough energy. It was that it produced energy in the right way, at the right rate, over the right timescale. Ordinary supernova power sources, like radioactive nickel decay, are fast. They release most of their energy early, and their luminosity falls off rapidly with a characteristic timescale. The Magnetar model, by contrast, predicts a more sustained energy injection, because the magnetar's spin energy is released gradually as the rotation slows, with the power output falling off in a way that matches the slower decline observed in superluminous supernova. The model was not just consistent with the observed brightness. It was consistent with the observed shape of the light curve, in a way that other models were not. But, for 16 years, it remained a hypothesis. The difficulty was that the model's central prediction, a magnetar spinning inside the supernova and depositing its energy, was hidden behind the expanding ejecta, inaccessible to direct observation. What you could observe was the light coming out. What you could not directly observe was the engine producing it. Until a graduate student noticed that a particular supernova's light curve was not behaving the way any model said it should. Under the standard Magnetar model, the light curve of a superluminous supernova, powered by a central spinning neutron star, should look relatively smooth. The Magnetar deposits energy at a rate that decreases as its spin slows due to magnetic braking, producing a roughly exponential decline in power output. This produces a light curve that rises, peaks, and then falls in a shape that is smooth, predictable, and well described by the model equations. Almost every observed superluminous supernova has bumps in its light curve, not small, marginal irregularities, but clear, repeated deviations from the smooth expected shape. These bumps were known. They were documented. Multiple studies had tried to explain them, invoking things like instabilities in the magnetar's magnetic field, interactions between the ejecta and surrounding material, or random variations in the engine's behavior. None of these explanations worked convincingly. They could explain one or two bumps, but not a sequence of them. And none of them made a specific, testable prediction about the timing of the bumps. When Farah looked at SN2N24A5's light curve, he saw something different from previous superluminous supernova. Not just bumps, but 5 or more clear, unambiguous modulations in the plateau phase, and those modulations were not occurring at random intervals or at a fixed interval. They were occurring at intervals that were decreasing. Each bump arrived slightly sooner than the previous one, following a pattern that was smooth and mathematically precise. This is not what any existing model predicted, and it is not what random processes produce. Random processes produce irregular variations. Mathematical acceleration of a periodic signal, a chirp, is what deterministic physical processes with specific geometries produce. Something specific was happening inside SN2N24A5, something with a precise mathematical structure, and the standard model had no account of it. There was just no existing model that could explain a pattern of bumps that get faster in time, Farah said. I started thinking about ways this could happen, because the signal seemed too structured to be due to random interactions. The investigation that followed Farah's recognition of the chirp pattern is worth tracing in some detail, because the strength of the final conclusion depends on understanding how carefully the alternatives were eliminated. The key constraint, which Farah's team recognized early, is that any model has to explain two things simultaneously: the period of the signal, the time interval between bumps at any given moment, and the period derivative, meaning how fast that interval is changing. A model that explains one but not the other is not the right model. The chirp in SN2N24A5 is precisely described by both quantities, and those quantities pin down the physics so tightly that most explanations fail immediately. To appreciate how constraining this two-quantity requirement is, it is useful to think about what it would take for a model to accidentally fit both. The period of the bumps is measured directly from the data. You count the time between successive modulations. The period derivative is measured from how rapidly those intervals are changing over time. These two quantities are related by the underlying physics, but are, in a statistical sense, largely independent measurements. Measuring one does not automatically constrain the other without a model. A model that has enough free parameters can always be tuned to fit any single measured quantity. But fitting two independent quantities simultaneously requires that the model's internal structure correctly captures the actual physical process producing the signal. A wrong model, however cleverly parameterized, will generally fail to fit both quantities simultaneously without requiring parameter values that are physically unreasonable or inconsistent with other observations. The team systematically worked through the candidate mechanisms. The first candidate was purely Newtonian precession, the kind of wobble that can be produced by ordinary gravitational torques without any relativistic effects. Newtonian precession can produce periodic signals, and it can produce signals with changing periods in some configurations. But the specific rate of period change predicted by Newtonian precession for any plausible combination of parameters for the disk and neutron star does not match what was observed. The chirp rate was wrong by enough to rule this out. The second candidate was precession, driven by the magnetar's own magnetic fields. A spinning magnetic star exerts torques on a surrounding disk through its electromagnetic interactions, and these torques can cause the disk to precess, producing periodic brightness variations. But again, the period and the rate of period change predicted by magnetic torque precession do not match the observed values. The magnetic field strength needed to produce the observed chirp rate would be inconsistent with other observed properties of the system. The third candidate, the one that fit, is lens-Thirring precession. Lens-Thirring precession is a prediction of general relativity, specifically of the frame dragging effect described in Einstein's field equations. A rotating mass, according to general relativity, drags the fabric of spacetime around it, like a stirring rho d drags the water in a glass, creating a kind of vortex in the geometry of space and time itself. Objects moving in this warped geometry are carried along by the dragging, causing their orbits and orientations to precess, to rotate slowly around an axis different from their own spin axis. To understand this intuitively, it helps to think of spacetime not as an empty abstract stage, but as something with physical behavior, like a very thick fluid. Normally, we think of gravity as a simple pull toward a massive object. Einstein's first great insight was to reframe this pull as objects following the straightest possible paths through a curved spacetime, rather than being pushed and pulled by a force. But Einstein's equations say something stranger still. A rotating mass does not just create this curvature, it also creates a rotational drag in the geometry around it, twisting spacetime in the direction of its own spin. Anything moving near a spinning mass is not just falling toward it, it is also being carried along by the twist. The way a leaf in a whirlpool is not just moving toward the center, but is also being rotated by the current. This is what Joseph Lenz and Hans Thirring predicted in 1918, less than 3 years after Einstein published his field equations. They showed that a rotating mass should drag spacetime around it in the direction of its rotation, and that this dragging while d caused the orbital plane of anything orbiting that mass to precess, to rotate slowly around the spin axis. The effect was named for them, lens-Thirring precession. For ordinary objects spinning at ordinary speeds, this effect is so small that measuring it for Earth required extraordinarily sensitive gyroscopes placed in orbit for years. The Gravity Probe B mission, launched in 2004 and finally reporting its confirmation of Earth's frame dragging in 2011 after decades of development. For a magnetar spinning hundreds of times per second, with a magnetic field 100 trillion times stronger than anything on Earth, the frame dragging effect is not a tiny correction. It is the dominant geometric influence on any nearby material. For a rapidly spinning magnetar, if there is an accretion disk surrounding it, material that has fallen back toward the neutron star after the explosion, and if that disk is not perfectly aligned with the magnetar's spin axis, the frame dragging torque C causes the disk to precess. The whole disk wobbles around the spin axis like a gyroscope that has been pushed sideways, maintaining its general orientation but rotating around the spin axis over time. This wobble is what periodically blocks and reflects the magnetar's light, creating the modulations in the light curve. The wobble produces a light curve modulation because, as the disk tilts through its precession cycle, it alternately blocks more of the magnetar's radiation output when the disk presents a larger cross-section to the line of sight, and blocks less of it when the disk is edge-on. Additionally, the disk reflects and re-emits radiation from the magnetar, and the geometry of this reflection changes as the disk wobbles. So, The observer sees both the direct radiation from the magnetar, variably blocked by the disk, and the reprocessed radiation from the disk itself, variably directed toward or away from the observer as the disk tilts. The combination of these effects produces a modulation in the total observed light that tracks the precession cycle. Crucially, the precession rate for lens Thirring precession depends on the radius of the disk. Material at smaller radii precesses faster. As the accretion disk's inner edge moves inward over time, as material is accreted by the magnetar and the disk SHR inks inward, the precession rate increases. This is exactly what produces the chirp, a signal whose period decreases over time, in a specific mathematical way determined by how quickly the disk's inner radius is shrinking, which itself depends on the magnetar's properties and the disk's mass. The full model has several parameters: the magnetar's spin rate, its magnetic field strength, the disk's mass and initial radius, and the rate of accretion. These parameters are constrained by other observable properties of the supernova, including its total luminosity, its spectral features, and the duration of the plateau phase. When Farah's team put all of these constraints together, they found that the lens Thirring model not only explained the chirp, but did so with parameter values consistent with all the other observations. No other model came close. As Farah stated, "We tested several ideas, including purely Newtonian effects and precession driven by the magnetar's magnetic fields, but only lens Thirring precession matched the timing perfectly." The paper was submitted to Nature and published in March 2026. It confirmed the 16-year-old Kaysen and Bildsen theory for the first time with direct observational evidence, and it did so through a mechanism, the specific mathematical signature of general relativistic precession, that the original theory had not even anticipated. Let's make three things concrete, because they are the foundation of everything that follows. First, what is a magnetar, and what makes it different from an ordinary neutron star? When a massive star dies in a core collapse supernova, the core is compressed into a neutron star, an object roughly the mass of the Sun compressed into a sphere about 20 kilometers across. The density inside is so extreme that ordinary atoms cannot exist. Protons and electrons are forced together into neutrons, and the resulting material is so dense that a teaspoon of it would weigh roughly 1 billion tons on Earth. Neutron stars spin rapidly, because as the core collapses its rotation speeds up, the same way a spinning ice skater speeds up when pulling their arms. They also have strong magnetic fields, compressed and intensified along with everything else in the collapse. Here is a way to think about the compression involved. The Sun's core is roughly 200,000 kilometers across. As it collapses into a neutron star, everything in that volume is compressed into a sphere 20 kilometers across. A reduction in linear size of Raug HLY 10 zeros, and a reduction in volume of roughly 1 trillion. Whatever rotation the core had at the beginning of the collapse is preserved as angular momentum, meaning the spin rate scales up by the square of the size ratio, spinning up to potentially 100 EDs of rotations per second from an initial rotation of roughly once a month. Whatever magnetic field existed in the core is similarly compressed, amplified by factors of millions to billions. The conditions that result, extreme density, extreme rotation, extreme magnetic fields, are among the most extreme in any ordinary astrophysical environment. A magnetar is a neutron star whose magnetic field is roughly 1,000 times stronger than an ordinary neutron star's, strong enough to snap the star's own solid crust in what are called starquakes, and to power emissions of X-rays and radio waves far more re-energetic than an ordinary neutron star. The magnetic field strength of a magnetar is roughly 100 trillion times stronger than the strongest magnet ever built by humans. At the distance of half the moon from Earth, a magnetar's magnetic field would be strong enough to erase the magnetic strip on every credit card on Earth. At that same distance, it would pull Te iron from hemoglobin in your blood, not a gentle effect, but a catastrophic one. These objects do not merely exist at the extremes of known physics, they define them. The rotational energy stored in a newly born magnetar, spinning hundreds of times per second, is enormous. It is this rotational energy, gradually transferred to the surrounding gas through magnetic coupling, that the Kaysen-Bildson model proposed as the power source for superluminous supernova. And it is the mechanical consequence of this spin, the frame dragging of spacetime, that Farah's discovery revealed as the source of the chirp. Second, what lens-Thirring precession actually feels like as a physical effect. Think of spacetime not as an abstract mathematical background, but as something with a physical consistency. A spinning object in spacetime does not just sit there. It drags the spacetime around it, creating a kind of current in the geometry of space and time, the way a spinning sphere drags water in a tank. Anything moving in that dragged spacetime is carried along by the current, and if something is orbiting in this dragged spacetime, its orbital plane slowly rotates, precessing around the spinning object's spin axis. For an accretion disk around a magnetar, this means the entire disk wobbles, not uniformly, but with an inner radius-dependent rate, as the frame dragging carries the orbital planes of the disk material through their precession cycles. The inner parts of the disk precess faster than the outer parts, and the net result, integrated over the whole disk, is a wobbling motion that periodically varies how much of the magnetar's light escapes versus is blocked or reflected by the disk. Each full wobble cycle produces one modulation in the light curve. As the disk shrinks inward, each cycle is faster than the last. The signal chirps. Third, what a chirp actually is as a mathematical object, and why it is so diagnostic. A chirp is a signal whose frequency, the number of oscillations per second, increases over time. The gravitational wave signal from two merging black holes is a chirp, because as they spiral closer together, they orbit each other faster and faster, and the gravitational wave frequency follows the orbital frequency. The signal from SN224 of FAV is a chirp, because as the accretion disk's inner radius shrinks, the lens-Thirring precession rate increases, and the modulation frequency of the light curve follows the precession rate. The mathematical shape of the chirp, specifically the relationship between the period at any given time and the rate of period change, encodes the physics of what is driving it. Lens-Thirring precession produces a chirp of a specific mathematical form. Newtonian precession produces a different form. Magnetic precession produces yet another. Farah's team could test each one against the data, and only lens-Thirring fit. This is why the conclusion is not merely something is wobbling, but specifically, lens-Thirring precession, driven by a spinning magnetar, is wobbling a disk. The mathematical fingerprint is that precise. This kind of constraint, where two independent pieces of information about the same signal, the period and the period derivative, must simultaneously fit the same model, is a powerful test. A model that fits only one fails immediately. A model that fits both, while also being consistent with the other observed properties of the supernova, is a model that is carrying information about the real physics. The probability that a wrong model would accidentally fit two independent, precisely measured quantities simultaneously is very small. This is why Farah's team could state, with confidence, that the lens-Thirring explanation is not just a possible interpretation, but the only interpretation consistent with the data. There is one more dimension to this story that the three concrete concepts above point toward, but do not fully express. The question of what it means for a theory to be confirmed in physics, and why this result represents something different from the MA-NY tests general relativity has already passed. When physicists talk about testing a theory, they generally mean finding a situation where the theory makes a specific, calculable prediction, measuring the relevant quantity precisely, and comparing the measurement to the prediction. If they match, the theory passes that test. If they do not match, either the theory is wrong or the measurement has an error, and subsequent work aims to determine which. General relativity has passed an enormous number of tests in this sense, but most of those tests have been in situations that Einstein, or his immediate successors, specifically anticipated. The precession of Mercury's orbit was a known anomaly that Einstein's theory immediately and precisely resolved. He worked it out himself in 1915. The deflection of light was a prediction Einstein made that was confirmed by Eddington's 1919 eclipse expedition. Gravitational waves were predicted by Einstein in 1916. Fina Eli detected a century later. Each of these represents a prediction made from the theory, tested against observation, confirmed. The lens-Thirring effect in superluminous supernova is different. It was not predicted, in the sense of being anticipated in advance. Nobody proposed looking for a chirping light curve in superluminous supernova as a test of lens-Thirring precession. Because nobody had a reason to expect such a signal to exist before Farah noticed it in the data. The confirmation came backward. A phenomenon was observed that turned out to require general relativity to explain, rather than a prediction being made and the end confirmed. This is a different kind of validation, not, we predicted this and it happened, but, this happened and we found that only general relativity can explain it. Both kinds of confirmation are scientifically valuable, but the latter carries a particular kind of weight. The universe is revealing, without being asked, that a theory correct in one domain is also correct in a domain nobody had thought to test. This is also why the result is not just a confirmation of general relativity, but a discovery about how magnetars work, how superluminous supernova work, and how the two are connected. The physics was there the whole time. It just took someone noticing an unusual pattern and refusing to be satisfied with the explanation that it was just random variation. Both parts of this story continue. The explanation of general relativity continues to find new applications in new regimes. And the dataset of superluminous supernova continues to grow, with new events being discovered and monitored by increasingly capable e-survey programs, each one a potential new laboratory for reading what the universe has encoded in its light curves. Here is why this matters beyond the specific case of SN224 of FAV. Superluminous supernova are not just spectacular objects. They are among the brightest events in the universe, which means they are detectable at cosmological distances, billions of light years away, well into the early universe. Astronomers have been coinciding whether they might be usable as cosmological distance indicators, similar to the type Ia supernova that were used in the late 1990s to discover the accelerating expansion of the universe. To use any class of explosion as a distance indicator, you need to understand what makes some of them brighter than others, and how their brightness relates to their other observable properties. If the Magnetar model is correct, and the brightness of a superluminous supernova is determined primarily by the spin energy and magnetic field strength of the central magnetar, then, in principle, The physics of the central engine determines the brightness. Understanding that engine more precisely, reading out its properties directly from the light curve, rather than inferring them only indirectly from the overall shape, opens the door to using these events as cosmic yardsticks in a more rigorous way. But the Magnetar model could not be used this way without knowing the engine was actually there, and actually spinning in the way the model required. SN 2024 of FAV is the first event where the engine's presence has been not inferred, but read directly from the Lig-HT curve, in a way that specifies the engine's properties from first principles through general relativity. Additionally, the discovery changes how we think about testing general relativity in extreme environments. Previous tests of lens-Thirring precession in astrophysical settings required either extraordinarily sensitive spacecraft, like Gravity Probe B, or observation of pulsars in specific binary configurations, where the orbital dynamics provide leverage on the precession. Superluminous supernova, if the lens-Thirring mechanism is confirmed in additional events, provide a new and independent test of FR aim dragging at extreme spin rates and magnetic field strengths, conditions that cannot be recreated in any laboratory, and that are qualitatively different from the conditions in which the effect has been tested before. The Kaysen and Bildsen paper was published in 2010 in the Astrophysical Journal. It proposed that newly born magnetars, spinning at hundreds of rotations per second, could deposit their enormous rotational kinetic energy into the surrounding supernova ejecta via magnetic dipole radiation, essentially using the magnetic field as a coupling mechanism between the spin and the explosion. The energy transfer rate would be highest early on, when the magnetar was spinning fastest, and would decline as the spin slowed due to magnetic braking. The predicted luminosities matched the observed brightness of superluminous supernova reasonably well. The predicted timescales matched. The paper was taken seriously immediately, and within a few years the Magnetar model was the leading hypothesis for The power source of superluminous supernova, cited in essentially every paper written on the subject. It is difficult to overstate how dominant this hypothesis became. For 16 years, the Magnetar model was the organizing framework for research into one of the most luminous class of astrophysical events known. But in science, a hypothesis and a confirmation are different things. The Magnetar model fit the broad shape of the light curves, the rise time and peak luminosity and overall duration. It did not uniquely explain the bumps, and without a way to observe The Magnetar directly, which was impossible because it was buried beneath billions of tons of expanding stellar debris, the confirmation remained out of reach. Other explanations were proposed and tested. Interaction between the supernova ejecta and a dense shell of material previously ejected by the star could produce extra luminosity and even some bumps. Instabilities in the magnetar's magnetic field could cause variations in the energy output. None of these alternatives were fully satisfying, and none made predictions specific enough to test against a chirping signal once that signal was recognized. What was needed was a supernova that was bright enough, close enough, and observed with high enough cadence that the detailed structure of the light curve could be resolved. SN 224 of FAV, at about 1 billion light-years, is nearby for a superluminous supernova. It was caught early, discovered by the LGO2 survey on December 12, 2024, and monitored closely over the following months by the Las Cumbres Observatory global network of telescopes, which can observe the same object from multiple sites around the Earth to get continuous coverage. The high-cadence observations, meaning observations taken frequently enough to resolve the detailed time structure of the light curve, were essential. Without them, the individual bumps would have blurred together, and T-chirp structure would never have been apparent. This is a point worth emphasizing, because it bears on how discoveries like this happen. The chirp was not hiding because it required more sensitive telescopes. Los Cumbres observatories instruments are not uniquely powerful by the standards of modern astronomy. What they provided, crucially, was continuous and frequent coverage. The global network allows observations around the clock without gaps, and the team's decision to trigger intensive monitoring of SN224 of FAV early gave them the time resolution needed to see the chirp at all. The discovery required asking the right question about the data, as much as it required collecting the data in the first place. It is worth dwelling on what a high cadence actually means in this context, because it is easy to underestimate how unusual the requirement is. For most astronomical transients, observing an object once a night, or once every few nights, is sufficient to characterize the basic shape of its light curve, the overall rise and fall. The bumps in superluminous supernova light curves were already known from this kind of observing. But a bump observed only once every few days is characterized as a bump, not analyzed for timing structure. To detect a chirp, a pattern of decreasing time intervals between bumps, you need to be able to measure those intervals precisely, which requires not just detecting each bump, but timing its onset, peak, and shape with enough resolution to distinguish a fixed period from a decreasing one. For the bumps in SN224 of FAV, which occurred over timescales of days to weeks, this required observations roughly every few hours or better during key phases of the evolution, coordinated across multiple telescopes to avoid the gaps that any single observatory's daylight and weather would create. The Los Cumbres network, with nodes on multiple continents in multiple time zones, provided exactly this capability, and the team recognized that they had an unusual event early enough to invoke it. Farah recognized the chirp pattern, built the lens Thirring model to explain it, confirmed that it required both the correct period and the correct period derivative to fit the data, and eliminated the alternatives. The 16-year wait for a smoking gun ended with a signal that the original theorists had not known to look for: a chirp, rather than a steady modulation, produced by a mechanism, lens Thirring precession, that the original model had not included. The power of the lens Thirring interpretation is not just that it explains the chirp. It is that it reads out specific properties of the magnetar from the signal. The precession period at any given time depends on the radius of the disk's inner edge, the magnetar's spin rate, and the magnetar's moment of inertia, which depends in turn on its mass and the still uncertain equation of state of neutron star matter. The rate at which the period changes depends on how quickly the disk's inner radius is shrinking, which depends on the accretion rate. These relationships are specific enough that fitting the chirp to the lens Thirring model constrains the magnetar's property ease. What the fit implies is a magnetar spinning on the order of hundreds to thousands of times per second, consistent with theoretical predictions for a newly born neutron star and with what is needed to power the observed luminosity. The disk mass and accretion rate implied by the period derivative are physically reasonable. The magnetic field strength implied by other aspects of the light curve is in the range expected for a magnetar. All of these parameters are consistent with each other and with the broader observational properties of the supernova. There is no free parameter that has been tuned arbitrarily to make the model fit. The lens Thirring model, applied to SN224 FAV, gives a self-consistent picture of a magnetar with specific, physically motivated properties powering a superluminous supernova. A picture in which the internal consistency of the various constraints on the model provides additional confirmation that the right physical mechanism has been identified. This is what makes the result compelling beyond the individual case. The Magnetar model, with lens Thirring precession as the mechanism generating the light curve modulations, makes specific, testable predictions. If you observe another superluminous supernova with similar bumps, and if those bumps follow a chirp pattern, the lens Thirring model should fit with physically reasonable Magnetar parameters. Future observations will test whether this is a general property of the class or a feature specific to events with particular initial conditions. There is a distinction that is easy to miss, but important to the significance of this discovery. The difference between using general relativity to describe the environment around an object versus using it to describe what the object itself is doing. Every major previous test of general relativity in astrophysics has been about the environment. The deflection of starlight by the sun, the precession of Mercury's orbit, the delay of signals passing near massive objects, the detection of gravitational waves from merging compact objects, the imaging of black hole shadows. All of these are tests of how spacetime geometry affects things moving through it. They confirm that Einstein's description of the gravitational field is correct in regions of strong gravity. It is worth being precise about this point, because it is subtle. When LIGO detected gravitational waves from merging black holes for the first time in 2015, the result was rightly celebrated as a confirmation of general relativity, and it was. But what it confirmed, specifically, was that Einstein's equations correctly predict the geometry of spacetime around two massive compact objects spiraling together, and that this geometry oscillates in exactly the way the equations predict, creating waves in space at imma that propagate outward at the speed of light. The merger was the source of the waves were the signal. What general relativity described was the spacetime geometry generated by the merger, the environment. Similarly, when the Event Horizon Telescope imaged the shadow of Sagittarius, * at the center of the Milky Way, what it confirmed was that the spacetime around a supermassive black hole has exactly the geometry Einstein's equations predict, producing a shadow of the specific size and shape expected. The black hole was the source. The image was the signal. What general relativity described was the geometry around the black hole, the environment. What is new in the SN224 of FAV result is that lens Thirring precession is being used to describe not the space around the magnetar, but the behavior of the magnetar disk system as a mechanical unit. The spinning magnetar is not just sitting inside curved spacetime. It is using the frame-dragging property of its own spin to drive the mechanical behavior of the material around it, and that mechanical behavior is directly observable in the light curve. The spacetime drag is not the medium through which a signal L propagates. It is the mechanism that drives the observable phenomenon. Farah's own characterization is precise. It is the first time general relativity has been invoked to describe the mechanics of a supernova. Not the background geometry of the spacetime in which the supernova occurs, not the spacetime around the magnetar, but the mechanical operation of the physical system at the supernova's core. What the magnetar is doing, and what that doing produces in terms of observable light. This distinction matters for what comes next. If lens Thirring precession is readable in supernova light curves, it becomes a tool for probing the internal mechanics of neutron stars in conditions that cannot be recreated in any terrestrial laboratory, and that cannot be directly imaged. The equation of state of dense neutron star matter, one of the fundamental open problems in nuclear physics and astrophysics. determines the relationship between a neutron star's mass and its radius. The moment of inertia, which enters the lens Thirring precession rate, depends on the equation of state. Future, high-precision measurements of the chirp pattern in superluminous supernova may provide new constraints on the equation of state, supplementing the constraints FRO-M gravitational wave observations of merging neutron stars. The two methods probe neutron star matter in different physical regimes and at different times in the star's life. Merging neutron stars at the end of a long evolution versus a newly born Magnetar are seconds after formation, and combining them provides more information than either alone. There are three frameworks in which the significance of this result can be understood, and they are not mutually exclusive. The first is as confirmation of the Magnetar model. Superluminous supernova are some of the most luminous events in the universe and have been poorly understood for years. The dominant theoretical framework said that magnetars power them, but this framework had survived without direct confirmation for 16 years. SN 224A FAV provides that confirmation, not just by fitting the overall light curve shape, but by revealing the engine's internal properties through a signal whose mathematical character unique, Li identifies it. The 16-year theoretical wait is over. There is a deeper significance here that is easy to miss. Scientific theories can survive for a long time as leading hypotheses without being confirmed, particularly when the confirmation requires observing something that is hidden, buried inside an explosion, inaccessible to direct imaging. The Magnetar model survived in this state not because it was uncontested, but because every alternative was equally hard to rule out. The data available before SN224A FAV could tell you that a Magnetar model was consistent with the observations. It could not tell you that it was the only explanation consistent with the observations. The chirp changes that. A chirp with specific period and period derivative requires a specific physical mechanism. It cannot be explained by any of the other proposed mechanisms. The confirmation is not just that the model works, it is that the alternatives do not. That is a qualitatively stronger result. The second framework is as a new application of general relativity. The domain in which general relativistic effects are physically important and observationally accessible has been expanding for decades. From the solar system to binary pulsars, to merging black holes to imaging black hole shadows. Lens Thirring precession, inside a supernova, detectable through the light curve of the event, is a genuinely new domain, qualitatively different from anything tested before. It is general relativity doing mechanics, not just geometry. This matters not just as a headline, but as a practical matter for the future of physics. Every time general relativity is tested in a new regime, it either passes, confirming the theory and constraining any alternatives, or it shows a discrepancy, which would be even more important. So far, general relativity has passed every test. But the tests so far have been concentrated in a relatively small number of physical regimes. The weak field solar system, the strong field merger environment of black holes and d-neutron stars, the cosmological scale of the expanding universe. A magnetar spinning inside a supernova represents a different regime: extreme spin, extreme magnetic fields, a specific kind of coupling between the frame-dragging geometry and the material that orbits within it. Testing general relativity here extends the domain of confirmed validity into new territory. The third framework, perhaps the most far-reaching, is as a demonstration that mathematical precision in a signal is itself physical information. The chirp in SN224 of FAV was not just an unexpected pattern. It was a message. The message was, A specific phi-sickle mechanism, with a specific mathematical structure, is operating at the center of this explosion. The message was encoded in the timing of light variations, and could only be read by someone who asked what kind of process produces exactly this mathematical signature. Farah asked, and the answer turned out to be Einstein. This principle, that mathematical regularity in an astronomical signal encodes the physics producing it, is not new. It is the basis of all spectroscopy, all pulsar timing, all gravitational wave analysis. But each new instance of it, especially one as striking as a chirping supernova explained by spacetime drag, is a reminder of how much information the universe is transmitting, and how much of it we receive but do not yet know how to read. Let's come back to where we started. A signal inside a supernova 1 billion light-years away, whose brightness oscillated in a pattern that kept accelerating, following a mathematical curve that did not fit any model based on ordinary physics. Only one model fit both the period and the rate at which the period was changing. And that model required that the fabric of spacetime itself, twisted by a spinning dead star at the center of the explosion, was making a disk of material wobble in a way no force in classical physics produces with this exact signature. The answer was not a coincidence. It was not an approximation. It was lens-Thirring precession, a consequence of general relativity, fitting the data precisely enough that all other explanations could be ruled out by the data alone. When this result was co-vered, most articles focused on two framings. Either astronomers confirm how the brightest supernova work, or dead star's signal follows mathematical pattern. Both framings capture something real but miss what is most interesting. The brightest supernova framing treats this primarily as a problem in stellar physics that has been solved. The deeper significance is that the solution required invoking general relativity in a context where it had never been applied before, not as a correction to Newtonian physics, not as a description of the spacetime environment, but as the fundamental mechanism determining the observable behavior of the entire system. The mathematical pattern framing implies mystery without resolution. In reality, the mystery is resolved, and the resolution is precisely what makes the result important. The chirp is not unexplained. It is explained exactly by lens-Thirring precession, and the explanation carries specific quantitative predictions that were tested against the data. Here are the specific things that most coverage missed. The distinction between environment and mechanics in general relativity tests. Previous applications of general relativity in astrophysics describe how spacetime geometry affects things moving through it. This result describes how the spinning magnetar's F-rame dragging property drives the mechanical behavior of the material around it. This is qualitatively different, and that difference matters for what it opens up. It is the difference between a law of physics being the context for what happens, and a law of physics being the mechanism that makes it happen. The 16-year gap between theory and confirmation, Kaysen and Bildsen, proposed in 2010 that Magnetar's power superluminous supernova. This theory was the leading hypothesis for 16 years without direct confirmation. The specific mechanism of lens-Thirring precession was not even part of that original theory. It was discovered in the data and then understood as the confirmation. The theory was right, but confirmed through a mechanism the original theorists did not anticipate. This is an unusual and important kind of scientific development. A framework that was established on indirect grounds, surviving for 16 years on the strength of consistency with broad observations, now confirmed through a completely unexpected direct signature. The theory did not predict the chirp. The chirp revealed the theory was right. The constraint on neutron star physics. The lens Thirring precession rate depends on the magnetar's moment of inertia, which depends on the equation of state of neutron star matter, one of the fundamental open questions in nuclear physics. The equation, OF state, determines what pressure a given density of neutron star material can exert, and this in turn determines the size and structure of a neutron star of a given mass. We cannot directly measure the interior of a neutron star, but the equation of state leaves signatures in observable quantities, like the lens Thirring precession rate. Future, high-precision measurements of the chirp pattern in other superluminous supernova could provide new constraints on this equation of state, connecting supernova Lig T curves to nuclear physics. This connection is almost entirely absent from popular coverage. What it means for using superluminous supernova as cosmological tools. If the Magnetar model is now confirmed with a mechanism that reads out the engine's properties directly, it opens the door to understanding what determines the brightness of these even TS, a prerequisite for using them as distance indicators at cosmological distances. And the simplest point of all. This is the first time anyone has used general relativity to explain the mechanics, not just the geometry, of a supernova. That is a genuinely new thing in the history of physics, and it is usually mentioned only in passing in popular coverage, if at all. NASA did not detect this signal. A graduate student at a relatively small telescope network noticed a mathematical pattern in a light curve, and kept asking why until the answer turned out to be Einstein. That is the actual story, and it is a better one than the headline. The Farah et al. Paper, published in Nature in March 2026, is the primary result, but its implications are already generating follow-up work in several directions. The most immediate is the question of whether other superluminous supernova show similar chirp patterns. The Farah paper analyzes one event with unusually high cadence observations. Most archival superluminous supernova light curves do not have the temporal resolution needed to detect a chirp, if one is present. The characteristic bumps in superluminous supernova light curves have been documented in many events, but the detailed timing structure within those bumps has not been analyzed for chirp signatures in most cases. The number of known superluminous supernova is still in the hundreds, a small sample compared to the thousands of ordinary supernovae studied each year, and the subset of those with cadence sufficient for chirp analysis is smaller still. Teams are now going back to archival data with this question explicitly in mind, looking for events where the observational cadence is sufficient to test whether the bumps show decreasing periods. This is not a simple exercise. It requires careful reconstruction of the timing from sometimes heterogeneous datasets, handling the gaps and systematic effects of different observatories and instruments, and applying consistent analysis methods. If chirp patterns are found in additional events, and if the lens Thirring model fits them with physically consistent parameters, the mechanism will move from a single event confirmation to an established feature of the class. If chirp patterns are not found in other events, that raises questions about whether SN224A FAV is a special case. Perhaps because it happened to have an especially massive or extended accretion disk, or because its magnetar was born with a particularly high spin rate, or because the geometry of the misalignment between the disk and the magnetar SPI n-axis was favorable for producing a detectable precession signal, or whether the disk conditions needed for lens Thirring precession to dominate only occur in some events. The October 2025 work from the GECAM team on SGR-J 1935 plus 254 provides a parallel line of evidence for complex mathematical structure in magnetar signals. That work examined light curves of Magnetar X-ray bursts from SGRJ 1935 plus to 1954. A galactic magnetar, and the first confirmed source of fast radio bursts, and found a new pulse-shape morphology, which they termed the exponential rise and cut-off decay Urquhart pattern, distinct from the previously dominant fast rise exponential decay model. This independent WO-RK, on a different magnetar in our own galaxy, using completely different instruments and observational techniques, suggests that the kind of mathematical precision evident in SN224 of FAV's chirp is not unique to that one event, but may reflect something more general about how magnetars encode their physics in the signals they emit. Future wide field time domain surveys will detect superluminous supernova at a much higher rate than previous surveys. The Vera Rubin Observatory's Legacy Survey of Space and Time, which began operations in 2025, will monitor the sky repeatedly with CAD CES that should be sufficient to detect the kind of time structure that Farah identified in SN224 of FAV. For the nearest and brightest events, Rubin is expected to increase the discovery rate of superluminous supernova by factors of 10 to 100 compound red to previous surveys, and will monitor them automatically from the moment of discovery. The combination of higher detection rates and better cadence should produce a much larger sample of events where chirp analysis is possible within the next several years. Not merely one event studied in depth, but potentially dozens or hundreds, enough to characterize how common the lens thirring mechanism is, and how it varies with the properties of the progenitor star and the resulting magnetar. This connects to the larger question of whether superluminous supernova can ultimately be used as cosmological distance indicators, alongside the type Ia supernova that enabled the discovery of dark energy in the late 1990s. Type Ia supernova are useful as distance indicators because their peak luminosity is standardizable, related to how quickly they fade, in a way that can be calibrated empirically. Superluminous supernova are intrinsically much brighter, which means they are visible at much greater distances and much earlier in the universe's history. If the magnetar model can be confirmed across a large enough sample, and if the relationship between the chirp properties and the peak luminosity can be established, it might eventually be possible to see them as more powerful cosmic rulers than type Ia supernova alone. The Farah result is the first step toward that goal, not the cosmological application itself, but the confirmation that the engine powering these events can be characterized from first principles. Here is what this story is really about. For over a century, Einstein's theory of general relativity has been one of the foundational achievements of human thought. It has been tested in increasingly extreme environments, always passing, always accurate, always confirming that the universe's geometry is as Einstein described it. The tests have been extraordinary. Clocks running faster in orbit, light bending around the sun, gravitational waves detected from merging black holes a billion light-years away, the shadow of a black hole imaged directly. All of these tests confirmed something about the spacetime environment, about how matter moves through curved geometry, or how energy propagates through warped space, or how the geometry evolves in response to mass. None of them described what general relativity does to the mechanics of an astrophysical process happening in real time, to the way material moves and behaves under the direct, active influence of a spinning mass dragging spacetime with it. SN224 FAV is the first event where general relativity is not just a backdrop, not just a correction, not just a description of the stage on which physics plays out, but a mechanism. The magnetar does not just exist in curved spacetime. It uses spacetime drag as a force, making a disk wobble in a way that no other force can produce. and that wobble is observable, measurable, and fitted precisely by Einstein's equations from 1 billion light years away. There is something worth pausing on about what, fitted precisely by Einstein's equations from 1 billion light years away, actually means in human terms. General relativity is not a simple theory. Its field equations, in their full form, are among the most complex equations in all of physics. 10 coupled nonlinear partial differential equations that relate the curvature of spacetime to the distribution of energy and momentum within it. In their exact form, they can only be solved analytically for a small n number of highly idealized configurations. The practical application of these equations to something as messy and complicated as a supernova environment, with an accretion disk, a rapidly spinning magnetar, strong magnetic fields, and expanding ejecta, requires approximations, numerical solutions, and careful matching between the theoretical framework and the specific observational constraints. And yet, when Farah's team applied this framework to the chirp in SN224 FAV, it worked. Not approximately, not roughly, precisely enough to rule out all the alternatives, to fit both the period and the period derivative, and to imply a self-consistent set of magnetar and disk parameters. The theory, developed on Earth a century ago from abstract mathematical principles, reached across 1 billion light years and correctly described what a spinning dead star was doing inside a stellar explosion. A graduate student noticed an unusual pattern in a light curve. He asked, what kind of physics produces this exact mathematical signature? The answer was the geometry of spacetime itself, twisted by a spinning dead star, acting as a mechanical drive for a disk of material, which wobbles and strobes and chirps its way across 1 billion light years to be recorded by a network of telescopes on the surface of a planet, orbiting an unremarkable star on the edge of an ordinary galaxy. And the chirp was Einstein, not an approximation of Einstein, not Einstein in the limit of weak fields. Einstein, exactly, in one of the most extreme physical environments in the universe, where matter is compressed to nuclear density, where magnetic fields are 100 trillion times stronger than anything on Earth, where the spin of a dead star drags spacetime fast enough to make the dragging itself a dominant mechanical effect. The universe has been running this experiment for as long as magnetars have been forming in supernova. We have only just learned to read what it has been writing. There is one more thread connected to this discovery. The magnetar at the center of SN224 FAV was born spinning rapidly, hundreds of times per second, and it will slow down over thousands of years as its magnetic field breaks its rotation. But some neutron stars, in a completely different evolutionary way, can spin up, gaining rotational energy from a companion star that feeds material onto their surface, until they are spinning hundreds of times per second again, in a way that is stable and precisely regular. These are millisecond pulsars, and the precision of their timing, some of them rivaling atomic clocks as the most accurate natural timekeepers known to exist anywhere in the universe, makes them a completely different kind of instrument for reading physical laws. A pulsar is a neutron star whose magnetic poles are misaligned with its rotation axis, causing beams of radio emission to sweep across the sky with each rotation, like the beam of a lighthouse. From Earth, we see a regular pulse of radio emission each time the beam sweeps past us, and the timing of these pulses is so stable that measuring even tiny deviations from perfect regularity can reveal the presence of planets. The effects of general relativity on the pulsars orbit around a companion star, and the subtle influence of gravitational waves passing through the galaxy. Arrays of these pulsars, spread across the galaxy and monitored over years and decades, acting together as a single enormous gravitational wave detector, have recently begun returning signals, suggesting they may be detecting the gravitational wave background (ND) produced by merging supermassive black holes throughout the cosmos. The same kind of mergers that a future galaxy merger like the Andromeda-Milky Way interaction might eventually produce, on timescales of billions of years. What those precisely timed signals can reveal, not just about the pulsars themselves, but about the gravitational waves passing through the galaxy, and about the behavior of spacetime over enormous baselines, is a story about a completely different kind of astronomical signal that follows a mathematical pattern. That is a story for another time. We started with a graduate student looking at a light curve and noticing that the bumps were accelerating in a pattern that should not have been there. Not random, not fixed period, but chirping, like a gravitational wave signal, like two black holes spiraling together, except here the source was a supernova 1 billion light-years away. Then, we followed the investigation. The systematic elimination of ordinary physics, the recognition that only lens-Thirring precession fit both the period and the period derivative, the confirmation that a spinning dead star was twisting spacetime itself and using that twist as a mechanical drive for a wobbling disk, and the paper in Nature that described it as the first time general relativity has been invoked to describe the mechanics of a supernova. We saw 16 years of a Magnetar theory waiting for a smoking gun, and found that the gun turned out to be a different kind of weapon than anyone expected. Not a bright flare or a steady pulse, but a chirp, a signal whose acceleration encoded the geometry y of spacetime directly into the light curve of a stellar explosion. And at the end, we arrived at what this story is really about. General relativity, a century old, tested more thoroughly than any other theory in science, doing something it had never been observed to do before. Acting as the mechanical drive of an astrophysical system, not just as the background geometry, not just as a correction to Newtonian physics, but as the physics itself. The result raises a question that is easy to miss in coverage of individual astronomical discoveries, but that this story makes difficult to ignore. How many other phenomena in the universe, how many light curves, how many pulse profiles, how many timing residuals in archival data, are carrying mathematical information about physical processes that nobody has yet asked the right question about? The chirp in SN 224A5 was sitting in the data. It was not hiding. The Las Cumbres Observatory had taken the observations. The bumps were clearly there. What was missing was someone who noticed that the intervals between bumps were not random, and who refused to accept that randomness as an explanation. The history of astrophysics is full of signals that were present in data long before they were recognized for what they were. Pulsars were initially dismissed as interference before they were understood as rotating neutron stars. Fast radio bursts were initially thought to be terrestrial before it became clear they were extragalactic. In each case, the signal was in the data. What changed was the question being asked of the data. Farah's discovery joins this tradition. The chirp was always there. The explanation, a spinning dead star using the geometry of spacetime itself as a mechanical drive, was always the correct one. It took a graduate student, willing to look carefully at a light curve and ask why the pattern was too precise to be random, to bring these two things together. Whether the chirp mechanism is common among superluminous supernova, or specific to events with particular disk and magnetar conditions, remains to be determined. The answer matters both for understanding what fraction of superluminous supernova are powered d by magnetars in the first place, and for understanding what physical conditions at the time of the explosion determine whether a lens-Thirring observable chirp is produced. Archival searches and new high-cadence observations will address this over the coming years. But the timeline depends on how many suitable events the current and upcoming survey programs capture, and how quickly follow-up resources can be directed toward them. The specific equation of state of neutron star matter, which the lens Thirring precession rate depends on through the moment of inertia, remains one of the most important open questions in nuclear physics. The constraints from SN224 FAV are promising T, not yet competitive with gravitational wave constraints from neutron star mergers, events like GW 70 in 1817. The first detected neutron star merger, which imposed constraints on the neutron star radius, and by extension, the equation of state, through the θ-L deformability of the merging objects. Superluminous supernovae probe the equation of state in a different regime. Immediately after formation, when the neutron star is hot and rapidly rotating, rather than after billions of years of cooling and spin down. Combining constraints from both types of observations could eventually triangulate the equation of state more precisely than either alone. Whether the disk properties inferred from the lens Thirring model are consistent with independent constraints from spectroscopy or other observational channels has not yet been fully tested. The disk, invoked by the model, material that fell back onto the newly formed Magnetar after the initial explosion, is a physically reasonable component of some supernova models, but is not directly observable through spectroscopy in the same way that the expanding ejecta is. Establishing whether this disk is consistent with all available observations, not just the light curve timing, is the next step in validating the complete physical picture. And the broader question of what determines whether a superluminous supernova produces the specific disk Magnetar configuration needed for lens Thirring precession to be the dominant light curve modulating mechanism remains open. The answer, almost certainly, depends on properties of the progenitor star, its rotation rate at the time of collapse, the structure of its outer layers, the amount of material available to fall back, and, perhaps, on the spin rate and magnetic field of the resulting Magnetar, which themselves depend on the progenitor's properties. Mapping out these relationships will require a larger sample of events with detailed observations, and theoretical models of stellar evolution and collapse that can predict which progenitors produce the conditions needed for an observable chirp. First, a signal's mathematical structure is physical information. The chirp in SN224 of FAV was not just unusual, it was precisely characterizable, and that precision narrowed the candidate mechanisms to one. Mathematical regularity in an astronomical sign AL is not decoration. It is evidence. Every time a signal is dismissed as a noise or a random variation, without careful analysis of whether the variation follows a mathematical structure, there is a risk of missing something real. The bumps in superluminous supernova light curves had been known for years without this kind of analysis being applied to their detailed timing. Farah's contribution was to treat the timing as data rather than as irrelevant scatter. Second, the most important confirmation of a theory sometimes comes from a mechanism the original theorists did not anticipate. Kaysen and Bildsen proposed the Magnetar model without including lens Thirring precession. The confirmation came through exactly why that mechanism. The theory was right for reasons partially different from the ones first proposed. This is not unusual in science. Theories are often confirmed through observations that the original proponents did not specifically predict, as long as the underlying framework is correct. The lesson is not to be overconfident in the specific mechanisms proposed by a theory, but to remain open to the possibility that a correct framework might be confirmed in unexpected ways. Third, High-cadence observations are not a luxury, but a scientific necessity for certain classes of discovery. The chirp, in SN224 FAV, would have been invisible without frequent enough observations to resolve the timing structure of the bumps. Infrastructure, your investments in global telescope networks and automated monitoring programs directly enable this kind of result. The discovery would not have been possible if Farah's team had been limited to once-per-night observations, or had faced the nightly weather gaps that afflict any single observatory. The investment in the Los Cumbres global network, built specifically for continuous time domain coverage, was the technical prerequisite for the scientific result. Fourth, general relativity has not finished being discovered. A century after Einstein, it continues to reveal new physical phenomena in new regimes, and the domain of its observable mechanical effects is still expanding. The theory is not just a framework for understanding things we already knew about. It is an ongoing source of new predictions about phenomena that have not yet been looked for, in conditions that have not yet been fully explored. Fifth, the universe is encoding physical laws in the signals it emits. We are not just observers of astronomical events. We are readers of physical messages, written in mathematics, transmitted in light, arriving from 1 billion light-years away, waiting for someone to notice that the pattern is too precise to be random, and to ask what it is trying to say. The universe does not explain itself. It presents data. Whether that data reveals its meaning depends on whether anyone is asking the right question. What does it mean for general relativity to describe the internal mechanics of an explosion, rather than just the spacetime around it? Is this a qualitative change in how we understand the theory, or another point on a continuum of increasingly extreme tests? The answer depends on what you think tests are for. If tests are about checking whether a theory is correct, this is another point on the continuum. General relativity has passed every test, and it passed this one. But if tests are about discovering new physics, about revealing phenomena that the theory predicts but that nobody had yet been able to observe, this result opens a new door. It demonstrates that the same theory that describes the orbits of planets and the ripples of gravitational waves also has something to say about the internal workings of stellar explosions. In a regime where the theory's mechanical effects, not just its geometric effects, are observable. The chirp was sitting in the data, waiting to be noticed. How many other signals in astronomical datasets might be encoding physical information that has not yet been recognized? Because nobody has asked the right question about the mathematical structure of the pattern. The history of astronomy suggests the answer is many. The cosmic microwave background contains encoded information about the conditions of the early universe. The spectra of distant galaxies encode the composition and motion of gas clouds billions of light-years away. The arrival times of pulsar signals encode the effects of curved spacetime on the propagation of radio waves. Each of these was, at some point, just a pattern in data that someone took seriously enough to analyze carefully, and on the most human level. A fifth-year graduate student noticed something in a dataset and kept asking why until he arrived at Einstein. What does that chain of questioning, from an unusual pattern to the deepest theory in physics, tell us about how scientific discovery actually works? It tells us that discoveries are not made only at the largest observatories or the most powerful instruments. They are made wherever someone is willing to look carefully at what the data is saying, and to refuse to be satisfied with the explanation that the pattern is not really a pattern at all. If this one stayed with you, let us know which part landed hardest. Was it the moment Farah recognized the chirp and knew it did not fit any existing model? The process of eliminating each alternative until only lens thirring remained? The realization, T, a spinning dead star, was using the geometry of spacetime as a mechanical drive. Or, the larger picture, a century-old theory doing something genuinely new, in one of the most extreme environments in the universe, readable from 1 billion light-years, oh wow why. And if you want more stories like this, real physics at the frontier, told carefully, subscribe to Galaxy Pulse. We will see you in the next one. 1 billion light-years away, a dead star was spinning. It was dragging spacetime with it. A disk wobbled, light flickered, accelerating, chirping. And across 1 billion years of travel, the signal arrived at a telescope, and a graduate student asked, "What kind of physics does this?" The answer was Einstein. It was always going to be Einstein.